In this video, we're going to derive the Fourier series coefficients for a particular waveform. The waveform that we're going to work with is a triangle wave. And here we have a triangle wave. It is periodic and goes on forever. And it alternates between +1 volt and -1 volt. And it has a period of t0 seconds. So it gets down to its minimum there at t0/2. Now, from the previous section, the previous video, we recall that we said that any periodic signal can be represented as a summation of these components or building blocks. And these components are DC signals and sinusoids at various frequencies. The reason we want to do this decomposition into these pieces is because we know how a linear time invariant system affects a sinusoid. We know that we can calculate a gain and a phase shift given a frequency. And we're going to do that for every component of a signal to put together the complete response. So that's where we're going with this. So any periodic signal can have a DC offset, and then it has a possibly infinite number of components of increasing frequency. And in order to get any phase combination, we start with the sine and cosine form. There are other forms that we will look at later in the chapter, but they're very closely related to this one. But this first one, we take our coefficient a sub n for each n times a cosine at a frequency. The frequency is n times the fundamental frequency. So the fundamental frequency is 2 pi over the period, the fundamental period of the waveform. So we're looking at higher frequencies that are integer multiples of this fundamental frequency, which means that the cosines will go through n complete oscillations when we go through one t0 period of the periodic function that we're working with. Now, because we can have any phase in a signal, the way we get it here is we mix together sine and cosine components at the same frequency. So here we have the sine component. We use the B coefficient for that. Same frequency, n times the fundamental, where n is an integer. And there's our time. We forgot our time variable there. Okay, so there is the complete expression. Now, the goal of Fourier analysis is for any periodic waveform, such as that triangle wave that we drew at the right, we want to be able to figure out what the A and the B coefficients are. Once we know the A and the B coefficients and how they relate to these sines and cosines, we can find the effect of any linear time invariant system on them using the material from the end of chapter 2 in section 2.7. So we derived on the previous video the following formulas. A0 is the DC value, so we average over one period. Now, the integrals that we gave you were 0 to t0 in the original formulas, but we explained that because these are periodic functions and they have period t0, that we can equivalently work over any period. So if we indicate any period t0, starting at any time and ending t0 seconds later, we show the integral in general in that form. In particular, for the triangle wave, let us take a look at the symmetry. It has a straight line segment for half of the period from 0 to t0/2, and it has another straight line segment, which is just a time reversed image of the other one from negative t0/2 to 0. So we're going to focus on the integral from minus t0/2 to t0/2 to simplify the form of the lines a little bit. If we were working with the period ending at t0 over here, we would have this line, and what we would have to do is we would have to find its intercept, which is -1, and work with that. But this one here will be a little bit simpler. So we're going to do our limits minus t0 over 2 to t0 over 2. We're going to do that for all of the, we're going to use those limits for all of the coefficients. And it's just the DC value. And we can see for this waveform, without actually having to go through the calculation, the positive and negative areas above and below the triangles cancel out, and that DC coefficient is going to be 0. We could prove that by doing this integral, but we would have the negative and the positive areas canceling out. Let's next take a look at the sine components. So here we have b of n is 2 over t0. When n is greater than 1, we have a 2 instead of a 1, as we derived last time. And we do the integral. Here I'll just indicate a period t0 of x of t, which is our triangle wave for this example, times the sine at n omega naught t. Now, sine is an odd function, and our triangle wave here is an even function. So we have an odd function times an even function. So we have an integral of an odd function. The odd function is the second one, so an even function, the x of t, and an odd function. And if we multiply an odd function by an even function, we get an odd function. And we said that we can do the integral over any period. So if we take the integral from negative t0 over 2 to t0 over 2, we will get the integral over a symmetric interval of an odd function is going to be 0. The positive time and negative time portions exactly cancel out. So all the b sub n's are equal to 0. So all the information about this function is going to have to be in the a sub n's, and that's what we're going to work on next, is finding the a sub n values for this triangle wave. So the formula for the a sub n is very similar to the b sub n, except we use the cosine instead of the sine. 2 over t0, integrate from negative t0 over 2 to t0 over 2, x of t times the cosine of n omega naught t dt. And let's sketch that triangle wave again. And now we're going to do one more simplification. We notice that the triangle wave is an even function, and we are multiplying it by cosine, which is an even function. So when we multiply two even functions together, we get an even function. And when we have integral of an even function over a symmetric interval, so we're looking at the even function at negative times and positive times, and we're integrating over these negative times and these positive times, the integral is going to be symmetric. We're going to get the same area contribution for negative times as we do for positive times. So we can simplify this integral a bit, and we can say that it is twice the integral from 0 to t0 over 2 of that quantity. So it's going to be twice that integral, and we had a 2 over t0 out front, so we'll have 4 over t0 here. And now we have x of t times cosine n omega naught t in the range 0 to t over 2. So now we need an equation for this line. So x of t in this range is 1 over, so that's the intercept at 1, and the slope is negative 4 over t naught. And we multiply that slope times t. So we see that it is decreasing by 2 volts in the time t0 over 2. So that gives us a slope of negative 4 over t0. So there we have an equation of that segment, and that is the expression in our integral. 1 minus 4 over the constant t naught times the time variable t times cosine of an integer n times omega naught t dt. N is a parameter, and we're going to carry it through here. N is telling us what frequency we have, and for each n that we evaluate in this integral, we will have a coefficient a of n that adds a cosine component to the sum that we use to build up this triangle wave. So now we're going to go ahead and we are going to start evaluating this integral. First thing that we're going to do is we are going to take care of the 1 in the x expression. So that's just 1 times the cosine on the right. So when we integrate that cosine, we're going to get a sine. So first of all, we have a 4 over t0 out front, and now we want to integrate that cosine times 1. So we're integrating with respect to t, so the coefficient of the cosine is going to come out as a constant out front. Now, before we go further, omega naught and t naught are related, and we don't want to express that as two separate variables. So what I'm going to do is I'm going to write omega naught as t naught over 2 pi, because we're going to need that relationship in order to do a number of cancellations. So we have cosine of t times this constant that we're integrating, and the constant is n times t naught over 2 pi. So when we integrate, that constant is going to come out front as a reciprocal, and we have t0 over 2 pi n sine of n 2 pi over t naught t. So that is the integral of the indefinite integral of the portion due to 1 times that cosine. And we're going to have to evaluate that portion from t equals 0 to t naught over 2. Because remember, we're just working in the second half of the period because we doubled the value of the integral to pick up the first half by symmetry of an even function being integrated. Now we have to handle the more complicated component, which is 4 over t naught times t. So there's t, our variable for integration. So we have t times cosine n omega naught t here that we are integrating. So this 4 over t naught is going to be a constant. So we'll pull that out front here, 4 over t naught, and we're going to have the integral. Let's just write it in this form, from 0 to t naught over 2 of t cosine n 2 pi over t naught t dt. And now we can work this expression and simplify it further. Multiplying this 4 over t naught into the first expression, we get 2 over pi n, and then we have sine of n 2 pi over t naught. And now let's evaluate the indefinite integral and make it definite. The t value at the upper limit of the integral is t0 over 2, and then we have the sine at the lower limit of the integral. T is 0, so all those other coefficients don't matter because sine of 0 times something is going to be sine of 0, and which is actually exactly 0 in this case. So that takes care of that first part. Now we need to also distribute this 4 over t0 over this second part, so we're going to get 16 over t0 squared being subtracted off in this second part. And now we have an integral of the form t times cosine ut dt. And let's just do a side calculation here. And you can find this in a table of integrals. T cosine constant t dt. The integral is a quotient cosine of ut, where u is a constant that is not dependent on the variable of integration, plus ut sine ut over u squared. So we're going to use that form here to integrate t times cosine of t, where the angle inside the cosine is scaled up by a constant. So we have, first of all, in our indefinite integral, the cosine ut. So we're going to have a big fraction here. And we have cosine of the constant u times t. So the constant is n 2 pi over t naught t. And then according to that integral formula, we add that to the constant times t times the sine. So I'll write the t first. The constant again is n 2 pi over t naught. And then we have the sine of what the argument. So n 2 pi over t naught t. And our denominator here is the constant squared. So n 2 pi over t naught squared. That is the indefinite integral. We are going to evaluate it from t equals 0 to t naught over 2. So now we'll simplify the expression working from the left. This first one, we cancel out the 2, we cancel out the t0, and we have sine of n pi, and then minus sine of 0, which is 0. And there'll be a few more simplifications coming soon. And now for this next one, let's take the denominator here and pull it out front next to this constant, because there'll be some simplifications there. So we have a multiplier of 16 t naught squared, and I will then have that denominator squared, and I take the reciprocal because I'm bringing it out front. So t naught over 2 pi n. We're going to get some simplifications there. And now we just have to take care of the numerator and substitute in the values for t to get the definite integral. Let's handle just this cosine term first, from the upper limit to the lower limit, and then after we do that, we'll handle this sine term separately from the upper limit to the lower limit. So handling the cosine term, we have a cosine at 2 pi over t0 times small t. Small t here is t naught over 2. So the t naught and the 2 both cancel out, and we're left with cosine of n pi. Then we subtract off that part evaluated at the lower limit, where small t is 0, so we're just going to have cosine of 0, which is going to simplify, of course, because that's equal to 1. Now let's take care of the sine portion. The sine portion has a 2 pi n over t naught out front. And now we have t times the sine of that argument. So at the upper limit, t is equal to t naught over 2, and then we have sine. And at the upper limit, we have that small t right here is getting replaced with t naught over 2. So it cancels out that t naught, it cancels out that 2, and we have left sine of pi n. And then we subtract off the lower limit, where small t is equal to 0, times the sine, and I don't care what it's the sine of because I'm multiplying it by 0 at the lower limit. And that is a simplified expression. Now we go further. If I'm simplifying this further, sine of pi times n is just 0, so that term disappears. So this could be sine of 0, sine of pi, which is 180 degrees, sine of 3 pi, which would be 540 degrees, so that's 1.5 times around the circle. Every time you go 180 degrees or pi, that sine is back to 0. So that first term completely disappears. And we are left with the second term. And now we will simplify. T0 squared cancels out this T0. 2 squared divides 4 into 16, so I have 4 left, and then I have pi n quantity squared. So here I have as the denominator pi squared n squared, and my numerator is -4, and now I have to evaluate what's inside this set of square brackets. On the side here, let's take a look at what's happening with the cosine of pi n term. So cosine of pi n is an alternating sequence. When n is 0, we get cosine of 0, so it's 1. When n is 1, we get cosine of pi, or 180 degrees, so it'll be -1. So every time n goes up by 1, we're moving halfway around the circle, or 180 degrees, so this sequence is going to alternate between plus and -1. So it's -1 to the n power. When n is 0 to 4, we have like 0, 360, 720 degrees, and the cosine is going to be +1. But when n is an odd number, we end up at 180 degrees, or 360 degrees more than that, and so on, and we'll get -1. So that's how we can simplify cosine of n pi. It's just -1 to the n power. So we have that -1 to the n power. Then we subtract cosine of 0, and then we add, and we cancel out the 2 pi n over t naught times t naught over 2, and all that's left there is pi n, and we multiply that by sine of pi n, and we can also make a simplification here. Sine of pi n is sine of 0 degrees, or 180 degrees, or 360 degrees. It's always going to be 0. So that term also vanishes, and we have times 0 here. And we can simplify a bit further. So we have -1 to the n power, which is going to be plus or minus 1, and then we subtract 1. So we're going to get either 0 or -2. And then we're going to get the -2s only when n is odd. Otherwise, it's going to be 0. So we get -2 times -4, and we end up with 8 pi squared n squared, and that only happens when n is odd, because then in the brackets we end up with -1, -1. So the bracket value is -2, and that gets multiplied by the -4, giving us the +8. If n is even, then the value of this a sub n is going to be 0. So we say otherwise, or o dot w dot. So this expression that we have right here can be found in the book, and it's presented in table 5-4 on page 210, and this is the formula given on line number 4. So that's where the formula came from, was evaluating these integrals for the Fourier series. So on the next slide, numbered components is because we found out that they were equal to 0. Because when n is an even number, right here, we had -1 to an even number. So that became +1. So we had 1 minus 1. So when n is an even number, the a of n becomes 0, and we don't need those components to make an approximation of this triangle wave. I show what happens for the various n's. So first of all, on the blue line, we have n equals 1. So that is a cosine at the fundamental frequency. And we can see there the cosine is going through a complete cycle on this example from -0.5 a second to +0.5 a second. So here on this example slide, we set the fundamental period to 1 second. And then we see that the cosine comes to a peak here, and it's not quite up to the triangle wave that goes up to 1, but it gets fairly close. The cosine is a rough approximation to that triangle wave, but it's not quite there. Then we add the cosine at this n equals 3 in this orange line. It has a much lower amplitude, but we have a positive value here, adding to our original positive value that is pushing us up closer to the peak of the triangle wave. Then we add in the value for 5 times the fundamental frequency. So here we have the cosine that goes through 5 complete cycles from -0.5 to 0.5, and it has a lower amplitude yet, but all these positive parts are adding up and getting us closer to +1 volt. Likewise, at the end of the period, all the negative parts are adding up, and in the light green here, we show the sum of the components 1, 3, 5, 7, and we see this light green one is getting fairly close to the triangle wave. It's still a little rounded off at the top. It gets up to very roughly 0.95 volts, not quite 1 volt, but as we add component 9, component 11, component 13, and so on, it's going to get closer and closer to that result. What I encourage you to do next is look at the MATLAB example that I have posted to go with this particular video lecture. There is code that will have MATLAB calculate the Fourier series, and it's going to do it 2 different ways. It's going to do it using symbolic calculus, so it'll show how MATLAB can do all the calculus we did on the last slide for you to help you find a Fourier series. And then it's going to evaluate the actual numeric values of the coefficients and add together the cosines to approximate the overall waveform that we have here. You can modify that and see what happens if you add in the component for n equals 9 and n equals 11 and so on. Remember, the reason that we are skipping the